Now in this equation we replace this term, by saying that this is equal to minus of this guy. Okay. And while doing that, so this u infinity that I took, this u infinity star, this is basically u star, x star, and then y star tends to infinity. Okay. Now, when we say y star tends to infinity, notice that this y star was your scaled coordinate. And how was the scaling? What was the scaling between y and y star? We took y as some delta times y star. Okay. And we know that delta over L was 1 by square root REL. So that means this delta is basically L times y star, or y is L times y star by square root of REL. Okay. So I want you to basically think about what exactly we are sending to infinity here. We are not sending y to infinity, we are sending y star to infinity. Okay. Here we are sending y star to infinity, but remember all of this we were doing when REL itself was much greater than 1. Okay. So a question arises, okay, if you are sending y star to very large values, your REL is also much greater than 1, then what about y? And indeed the question is right, you're right to ask that question, and we say that y is some finite quantity, finite y is some finite, let us say length or distance from the wall. So y will not be very far away from the wall, it is just that you will be outside the boundary layer. This y will be outside the boundary layer. So essentially this u infinity, remember this u infinity is from y star tending to infinity. This is your outer solution. This is your outer solution where your u star is this guy. Okay. Basically this is, so this u star is defined inside the boundary layer. So technically what you are saying is that when we used to do that matching of asymptotic solution, so if you recall we did the matching y and this is let us say u, and for that simple example of ODE we said that okay, your solution let us say looks something like, how was the solution look? Yeah, okay, the solution looks something like this. Okay, and we had an outer solution and we had an inner solution. Okay. So the idea is that this u infinity star, okay, this u infinity star is for scaled y star coordinates tending to infinity. So essentially this is at the edge of inner solution, or it is exactly the place where you would do your asymptotic matching, that your u inner for y let us say scaled y which was c tending to infinity equals u outer for y tending to 0. Okay. So it is this value, this u infinity star. So the reason why I am saying this is because in these kind of analysis, okay, in the analysis where we have u infinity star varying with x star and y star, okay, you have to remember what kind of y star you are looking at. What is the non-dimensionalization you have used for this y star? If you are using this non-dimensionalization for y star based on delta, if your non-dimensionalization is based on delta, then you have to send this y star to infinity, which is basically this in our case. Okay, and this guy will be basically y by L. Okay. So if you are solving the non-dimensional Navier-Stokes by taking L as characteristic length in both x and y directions, in that case you will have to solve for very close to the wall solution, which is the ideal flow solution close to the wall, and that becomes a top boundary condition for the boundary layer. So, if you have a boundary layer which is forming here and you have this outer inviscid solution, then you have to calculate the inviscid solution very close to the wall, and that becomes the outer edge equation of the inner layer. That because for the inner layer you have the wall condition and the other boundary condition is the outer edge layer. So, something like this. So, you have this as the inviscid flow and this is your, let us say, boundary layer, and when we do this, when we write this condition, we are somewhere in this regime. Okay, this condition is written in this regime. It's not written all the way to y tends to infinity. This is not at y tends to infinity, this is at y star tends to infinity, and that is important. The reason why that is important is because, so let us think about, say you have a case like this, which is something that we will treat in under Faulkner-Skan boundary layers. So, let us say you have a flow which looks like this. Okay. Basically, it is very similar to your flow in a wedge if you consider the wedge angle to be pi by 2. Okay. This is called a stagnation point flow. Basically, you are impinging flow on a normal flat, on a normal plate. Flow is not grazing past a flat plate, flow is hitting the plate. Okay. This is called a stagnation point flow. Now, in this kind of a case, when you try to solve for a boundary layer, let us say due to this kind of a flow, we will see in a minute what happens to the boundary layer, but what you have to remember is whatever ideal flow that you solve, this inviscid flow that you solve, it's going to be, let's say this is y, this is x, you have to obtain the limit of this inviscid flow for y tends to 0, and that becomes this condition. So, you have to evaluate the flow, the inviscid flow for y tends to 0 and use that here. This is not technically u infinity star where this is u star with y tending to infinity. You have a y star where y star itself is a scaled coordinate. So, you are sending already a stressed coordinate to infinity. So, in the usual coordinates which is y, or let us say y by L, if you look at this y by L, technically y by y is some finite length from the wall. So, y by L is a finite number. Okay, but still small. Okay, so this is very important that you will solve the inviscid flow in the wall limit tending to the wall, and you will use that as the boundary condition, as the top boundary condition for the boundary layer. Okay, which is exactly what we did in our matching. So, that should basically eliminate any doubt that okay, what happens to the y direction velocity due to the inviscid flow, because if you have u infinity star that is varying with x star, if your streamwise velocity is varying in x direction, then continuity dictates that you need to have some y direction velocity. Okay, if your del u by del x is not 0, then del v by del y cannot be 0. Okay. So, if you have v equal to 0 at the wall, del v by del y is not 0. So, v will become some finite number at some point of time, at some point in the space. So, if your u infinity is a function of x, then v has to be there, but you are solving your inviscid flow in the limit of y tends to 0. The outer coordinate y is tending to 0, where you know that you are going to impose, you are going to basically say okay, normal flow is 0. Okay. So, let us, having said that, let us look at our cases where basically cases like this, but more generalized, where we say that this u star del u star by del x star so here we say u infinity star del u infinity star over del x star, or rather d plus del. And now what we are going to entertain is What if this du infinity star by dx star is not 0? What happens in that case? Basically, the question that we want to ask under the confines of our theoretical analysis is, if du infinity star by dx star is not 0, can we find self similar solutions? Okay, and as you will see, we cannot find self similar solutions for any random, any variation, any functional variation of u infinity star. There are very particular variations of this u infinity star in x star which result in a self similar solution. Okay, so what we will do is we will say, so if you recall, in flat plates, without pressure gradient, we said that u star is sum f of f prime of eta. Okay, this is how we wrote. So in this case, I am going to say u star is sum u infinity star x star, which is this guy, times this f of f prime of eta, where this eta is y star over delta of x star. Okay, and soon, immediately, basically we make the make our life simpler by dropping all the stars for dimensionless variables. So anything that we discuss from now on, at least in this lecture, will be dimensionless, but I won't be putting stars so that I can write a bit quicker. So dropping these stars, we have the equation u as u infinity of x f of eta, and our governing equation is that along with the continuity equation. So continuity equation says this: y is still eta is still y over delta of x, and so del v by del y we can find is minus del u by del x, which is minus of du infinity over dx f prime, and then plus u infinity f double prime and then a y over delta square with a minus sign d delta over dx, and this is basically minus of du infinity over dx f prime, y by delta square is eta by delta minus u infinity f double prime eta over delta d delta over dx. This is your del v over del y. Now we know del v by del y, we can change it to eta, okay, using this. So del v by del y is basically del v over del eta times del eta by del y, which is 1 by delta x. So this becomes, so let's take this minus inside. So we write u infinity f double prime eta over delta d delta over dx minus f prime du infinity over dx, and then I multiply this with delta. So del v over del eta is u infinity the good thing about this is that, so your independent variables are, instead of x and y, they are now x and eta. Your independent variables are x and eta instead of x and y. So I can just perform this integration, okay. I can perform this integration, and what will I get? So what do I get when I perform this integration? So v is, so if you look at f double prime eta is nothing but f prime eta prime, which gives me f double prime eta plus f prime, right? So minus f prime. So this f double prime eta is nothing but f prime eta prime minus f prime, or this f double prime eta. So I can basically complete the derivatives in eta in both the terms. So I can directly write v is going to be u infinity f prime eta d delta over dx, and then a minus of u infinity f d delta over dx, and then you have from here minus of, so f prime integral with eta will be f delta du infinity over dx. We can combine these two terms to write this as u infinity f prime eta d delta over dx minus f d by dx of u infinity delta. So this is what we have for v. Now we can move and substitute in our momentum equation. So we are going to drop stars from everywhere here, and so we will need del u by del x based on this. So u is u infinity x f prime. So del u by del x is du infinity over dx f prime plus u infinity f double prime minus eta over delta d delta over dx. Okay, convince yourself that this is what we get. Just do the differentiation, and maybe if my algebra is wrong, please point it out. This is del u by del x. Del u by del y is straightforward. And del 2u by del y square is also straightforward. Most of this self similarity and all of this is just algebra. As you can see, it's basically just substituting your guess. So this is where the physical intuition and theory ends. All of this rest of all of this is just algebra. Okay, so if you can follow this correctly in your exams, then hopefully you won't have a very hard time in these kind of problems, because this guess is something that I'll be giving. Okay, I'll be giving you the starting point where to start. So most of these problems will be just doing the algebraic steps properly. So we can substitute this in our governing equation and we'll get, so u del u by del x gives us u infinity f prime times f prime du infinity over dx minus u infinity f double prime eta over delta d delta 1. It's just substitution, mindless substitution that's going on here. And then we have this, maybe I'll draw a line here. So I'll ask you to simplify this, so please note this down correctly. This times, so this was v, then you have to multiply this with, oh, del u by del y is actually easier, so I can just write it here, and that is u infinity f double prime over delta equals, we have u infinity du infinity over dx plus del 2u by del y square, which is this guy. So please simplify this and tell me what is the simplified equation that you get. So what is the simplified equation you get? So you can quickly multiply this whole equation by delta square by u infinity, delta square by u infinity. Okay. So that you see a lot of u infinities and deltas going away. So if I do that, multiply this whole equation by delta square by u infinity, then I get on the right hand side f triple prime plus delta square du infinity over dx equals. Now let us look at the right hand side. We get delta square f prime times f prime du infinity over dx minus u infinity. So just hang in there with all of this algebra. We'll quickly reach a very nice, some very nice conclusions. Delta f double prime anything cancelling out? Are there terms cancelling out? Huh? Are there terms cancelling out? So we have this, right? Delta. So this gives us delta f prime f double prime eta d delta by dx. Delta f prime f double prime eta d delta by dx with a u infinity. So these two terms actually will cancel out, and you will be left with delta square f prime square du infinity over dx minus delta f f double prime d by dx of. And now I can bring this on the left hand side and write the equation as. So I can take the delta square du infinity by dx common here, plus f f double prime so this is the equation that I am left with. Now again we are trying to find under what conditions can we find a self similarity solution, okay, or self similar solution. We are trying to determine those constraints. We are not trying to solve for boundary layers under flows which have any variation in x, okay. We are not prescribing what is u infinity as a function of x and then trying to solve for the solution, because that is technically not possible for us, because these are nonlinear PDEs and we do not have a general way of solving the solution. But we have one way of solving these equations, which is finding the self similar solution. So we are asking the question, okay, this is what I know how to solve, under what cases can I do this solution. They may not, this solution, the self similar solution may not apply to all u infinity as function of x, but I am trying to find, okay, under what conditions, under what u infinity as a function of x can I find a self similar solution. So first condition of being able to find a self similar solution was what? What should this equation be? This should be an ODE in eta, right? This equation should be an ODE in eta. So if this equation has to be an ODE in eta, that means x and y should not appear. Okay, our scaling of y by delta x should be such that we have converted a PDE into an ODE. Under what conditions can this be an ODE? What are those conditions? The conditions are that this delta square du infinity by dx is some constant, let us call it as beta, and this delta d by dx of u infinity delta is also a constant, let us call this alpha. Under the conditions that these are constants, this equation is a ODE, right. This equation is an ODE, and this equation, the f triple prime plus 1 minus f prime square times, let us say, beta plus f f double prime times alpha, this is called your Faulkner-Skan equation. and you can quickly see that this is a more generalized equation or generalized version of Blasius equation. Why? Because in Blasius, what was the first thing we had? U infinity was constant in x, right? U infinity was constant in x. The moment you put U infinity as constant in x, beta is 0, and this goes away, and you are left with these two terms which were in Blasius equation, which was the Blasius equation. Okay, so this is a more generalized form of Blasius equation. These are called Faulkner-Skan equations for different combinations of this alpha and beta, and we'll quickly see what these alpha and betas actually do. Yeah. Okay. So using these, we can actually determine what is the significance of this beta and alpha in terms of these these delta and u infinity. So these are two equations, by the way, for delta and u infinity, two equations for two variables. So we can solve what is delta as a function of x and u infinity as a function of x from these two equations. And the way we can do that is basically just look at this term. There are multiple ways you can do that. So this is one way that I like to do. So look at this term d by dx of u infinity delta square, and this is basically delta square du infinity over dx plus a 2 delta u infinity d delta by dx, and that I write as 2 delta, rather 2 delta d by dx of u infinity delta minus delta du infinity over dx. Hmm? Yeah, so that as I said, so we are not solving for a general case because that is nearly impossible because our PDE is a nonlinear PDE. We know a way of solving this equation or a way of reducing this equation to more solvable form. So we are trying to determine under what conditions I can do that reduction, because a general solution anyways, if you want to do, you will have to do it numerically, discretizing your space in x and y, and then solving that equation. That you can always do. Even here, there is no solution, there is no analytical solution for any general alpha and beta, as you will see. But solving this equation is obviously better because self similarity conveys a lot more than that equation. If you remember our discussion on self similarity of these boundary layers, then at different x locations, I can find a way to scale my experimental data to fit them all on a single curve. Okay. So, self similarity is important in that way that it helps us determine under what conditions can I eliminate the need of taking a lot of redundant data. Okay. So, we are trying to find those cases under which I do not need a lot of redundant data. I can basically find a x location where I can measure the boundary layer profile, and then I can extend that to any other x location using self similarity. So, if you look at this, okay, if you look at this delta should be outside, it should be 2 delta. So, here I am writing basically u infinity d delta by dx like this, which is what you get from here. And the reason why I am doing this is because these terms I know directly. So, this delta square du infinity by dx is beta, and then again you get a 2 delta times delta square delta du infinity by dx, that is again a beta, right. There is a 2, and then a delta times d by dx of u infinity delta is alpha. So, this is basically alpha minus beta, or 2 alpha minus. So, this term, the combination d by dx of u infinity delta square is 2 alpha minus beta, which means delta is square root of 2 alpha minus beta times x over u infinity. And this is very important because this equation conveys to you how is this delta changing in x, how is this delta that you have found, this scale delta that you have used for cell similarity, how is that changing in x. For constant u infinity, this is a square root x variation, okay, but for other variations of u infinity, this will not be necessarily square root of x variation. This can have any kind of a variation depending on how this u infinity is varying, okay. So now once we have this variation for delta, you can substitute that here. So let us do that. So let us do that. Let us substitute delta in this equation. So delta square is 2 alpha minus beta by u infinity x, and then we have a du infinity over dx equals beta. So that means 1 by u infinity du infinity over dx is beta over 2 alpha minus beta 1 by x. What do we get from here for u infinity? Hmm? What do we get from here for u infinity? So u infinity is some, let us say u naught x to the power beta over 2 alpha minus beta, where let us say this u naught is some known value at some x, okay, maybe x equal to 1 you can say. Yeah. That is what we assumed from the beginning, no? This delta is different from that delta star, which was the characteristic length. That was delta star, okay, or you can call it other. If we took, I don't know if we took it delta star or delta, what was it? Delta, okay, that was different, okay. Technically here you don't see stars because I am dropping the stars, so technically that should be delta star, okay, and that delta star x is basically some, so this is dimensionless, so this is some basic this is some boundary layer thickness, let's call it as delta b of x over this delta, which is this characteristic length. So I'm let's not, I didn't write that because otherwise you'll get confused in what is delta, where is delta star, so there should be delta star here, okay. So remember that we have dropped the stars anywhere. If you see after this point, it should have a star, okay. We are putting stars for dimensionless quantities. All of these quantities are dimensionless, okay. This u infinity is also dimensionless. All of these quantities are dimensionless. And now we are in a state where if you recognize this, okay, basically what you are saying is that on this edge of the boundary layer, on this edge of the boundary layer, you have this u infinity that is varying in the streamwise coordinate like this, okay, and only in those cases you can find the cell similar solution when this u infinity is varying as a power law of x, okay. This is varying as a power law of x. I can write this u infinity as, let us say, some u naught x to the power m, okay. And remember, when we were writing the Blasius equation, if you recall, there was a degree of freedom. There was an arbitrary constant which you can pick any value, you will have a different cell similar solution, but when you go ahead and dimensionalize your solution it will be same. Okay, there was an arbitrary constant that we chose as 1. Okay, here also you will have that arbitrary constant. Okay, both alpha and beta will not be unique. Okay, so what we can say is, let's say u naught u infinity is some u x to the power m, and let 2 alpha minus beta be 1 and beta be equals to m. This is an arbitrary choice. This is an arbitrary choice. Okay, this is an arbitrary choice and it does not affect your full dimensional solution, eventual dimensional solution, which is of practical interest. The dimensional less solution will change a little bit based on how your eta and all these things scale. Okay, because delta has this 2 alpha minus beta. Okay, that thing will change, but other than that nothing will change, and you can convince yourself by doing a computational solution of this equation or the Blasius equation. So in this case I can write this equation as f triple prime plus 1 minus f prime square. Now beta is nothing but beta is m actually, and then alpha is 1 plus m by 2. So this is how sometimes you will see this Faulkner-Skan equation written in some textbooks. Actually the textbooks which are dealing just with boundary layers, in those textbooks you will see it written like this, because this coefficient m directly means what kind of inviscid solution you are looking at. Okay. So we can find cell similar solutions if our u infinity, which is the streamwise velocity, is varying as a power law of x. What are the cases that we have seen where we have seen this power law variation? Have we seen this power law variation anywhere? If you recall, when we were looking at flows in the wedge, so if this angle is pi by m, then phi was some constant times r to the power m cos m theta. The velocity potential was this. Okay, let us for a minute, instead of m, let us write as m plus 1. If phi is given like this, then the radial velocity is del phi over del r, okay, which is some constant. So of course this constant is c naught times m plus 1, but I am not bothering myself with that. And then u theta is, and that becomes minus u naught r to the power m sin m plus 1 theta. Okay. Now if you recall these walls, so this wall is basically theta equal to 0 and this wall is theta equals pi by m plus 1. On both of these walls we actually satisfied the boundary condition that u theta is 0. We were looking at ideal flow, we were looking at inviscid flow, ideal flow. The only boundary condition that it can satisfy is the non penetration boundary condition, no slip is not there. Okay. So u theta is 0 on both of these walls, and let us say I orient my x direction like x coordinate like this and y coordinate like this. Then if I orient my x coordinate like this, then at theta equal to 0 I have u theta is 0, which is basically u y or v equals 0, and I have u r as u naught r to the power m, and then theta is 0. And what is the radial direction, radial coordinate in x, in this on this wall? It's x. So this is basically u equals some u naught x to the power m. So, essentially what we have found in Faulkner-Skan boundary layers is, sure, we found this inviscid solution. What about the boundary layers along these walls? Because in actual flows you will have a boundary layer also close to the wall. So, we have in a way found the equation for the boundary layers here. Okay, and a very interesting case for those boundary layers is what I had drawn earlier, is for m equals 1. I mean, it's interesting to me. Of course, there are other cases also, but this is something that I do want to point out, because for m equals 1, your u infinity is u naught x. Okay, and when m equals 1, what is this angle? What is this angle? So, basically, we are looking at a case like this. When m equals 1, we are looking at this stagnation point flow. Okay, and if you orient our axis x axis like this, then your u infinity, which is at this, let us say, boundary, this is the zooming in that you do for boundary layer, and you find that u infinity is actually some u naught times x. But the interesting thing that happens is here. What about delta? What can you say about delta for m equals 1? What can you say about delta for m equals 1? It's constant. So, this boundary layer does not grow for m equals 1. There is a constant boundary layer that you see at this wall. Okay, there is a constant boundary layer that you will see at the wall. So, now the question may come that how do you say this delta of x is your boundary layer thickness? How do I say that this delta of x is my boundary layer thickness? And basically the reason why I say this delta of x is boundary layer thickness is because whenever we send that eta to infinity, whenever we send that eta to infinity, we are applying those boundary conditions which are at the boundary layer edge, if we recall. Okay, I am applying those boundary conditions which are at the edge of the boundary layer. Okay, so the scaled coordinate, the y here is the scaled coordinate y star. I am sending that to infinity. Okay, again, every time whenever you think about these boundary layers, it's very difficult to visualize asymptotics without that helping ODE equation that I solved for you. Try to visualize that solution always. Okay, whenever I'm sending the inner coordinate or the scaled coordinate to infinity, I'm not going to the other boundary. I'm not going to actual y tends to infinity. I'm going towards the edge of the inner layer. Okay, I'm going towards the edge of the inner layer, and that is important. Okay. In some approximate solution finding techniques, what you will see is people apply, instead of eta tends to infinity, they will apply that boundary condition at eta equals 1. Okay. And if you look at all of these solutions, either Faulkner-Skan or Blasius, and you compute the numerical solution of these equations, you will find that this f prime will tend to 1 very quickly for not very large values of eta. It will start becoming very close to 1 for some finite values of eta, like 1, 2, 3, 4, 5, whatever 1. Whatever constant you pick here, for example, this 2 alpha minus beta, whatever constant you pick here, this f prime value starts becoming 1 very very early on. You don't need very large etas for this f prime to become 1. And that's how we know that this delta of x is in some sense representative of the boundary layer thickness. There is also an interesting case, okay. There is also an interesting case where, of course, this is there, and you can also have, let us say, you have a plate, and then you have a source, you have a sink here, okay. You have a flow sink here. So whenever you have a sink, you can, for that sink also, you can find the ideal flow solution, okay. Sinks and sources are very straightforward, you can find the ideal flow solution, and in that case you will see that this u infinity will vary as 1 over x, okay. In that case you will see this u infinity varies as 1 over x, and that is one of the particular cases where actually an analytical solution of this equation is possible, okay. The analytical equation solution of this equation is actually possible in that particular case, and you can look at that in the textbook. Any questions so far? So if you solve this equation, this one, or the Blasius equation where m is basically 0, so this term is not there but other terms are there, right. If you solve that equation, you will see, where should I draw? Maybe here I can draw. If you solve that equation and you plot f prime versus eta, you will see this is how f prime varies, okay. And very quickly it starts to approach 1. So these values of eta are not that large actually. What I am saying is these values of eta are very much like 1, are order of magnitude 1, okay. So you can write that order of magnitude of eta is actually 1 here. Physical meaning is that for eta around 1, your f prime is very close to 1. Eta being approximately 1, what does it mean here? Y is of the order of magnitude of delta of x. It's, I'm not saying it is boundary layer a priori. I'm saying by looking at that solution, you conclude that this delta of x is a boundary layer thickness. Y being very close to delta x, or let's say y being like delta x or 2 delta x or 3 delta x, you see that your u is approaching this u infinity, and that's how you say that it is the boundary layer edge, okay. It is not equal to the boundary layer edge, it is some measure of boundary layer thickness, okay. Actual boundary layer thickness might be some constant times delta of x, okay, but that constant won't be very huge or very small, that constant will be order 1, that's what it is trying to tell you, okay. And that you know only after looking at the solution of these equations, you cannot know that a priori, that's the whole point here. Now there are some other important concepts when we look at boundary layers, okay. These concepts are again of a lot of practical use, especially when it comes to modeling, and let me maybe start those concepts here. So there is something called a displacement thickness that you can form, and the definition of this displacement thickness is given as, it's basically this u in 0 to infinity. So it's written as star. Let's not write it as star. Let's write it as something else, because we have been using these stars for dimensionless quantities. Okay. In literature, you will see it written as displacement thickness in textbooks. Okay. For us, let's write it like delta hat maybe. And it is basically this quantity. Now you will want to ask the question, okay, what does it mean? What does it mean for this quantity to be looked at? Why is it very important? Why is it very useful? Okay. In some sense, if you plot u by u infinity, how is it going to look like in y at a particular x location? Let us say, how is this u by u infinity, u minus 1 minus u by u infinity, how is this going to look like versus y? It is going to start from 1 because u is 0 at the wall, right, and it is going to approach 0 like this. Now you are integrating basically this over y. So you are basically finding this area under this curve. Okay. Notice that 1 minus u by infinity is dimensionless essentially. So the dimensions of this area are that of a length. Okay. The dimensions are all fine here. Okay. So what why does this why is this called a displacement thickness? What does it even mean for it to be called displacement thickness? For that, what we can look at is actually the continuity equation inside your boundary layers, which is simply this. Okay, now I am back to dimensions by the way. So now I am, let's say, undropping the stars. So any quantity here on, if I am not putting a star, it is a dimensional quantity. So inside the boundary layer, you still have this as the continuity equation, and so del v by del y is minus del u by del x, and if I integrate this, then I see that v is basically v at a particular y. So this I can integrate from 0 to y, this I can integrate from 0 to y, v at 0 is 0. So v at a particular y is nothing but this guy. Okay. And you can basically write it like this. You can do this change of differentiation, because if your y is not a function of x, these are all independent coordinates. So you can bring the del by del x here. Okay, you can bring the del by del x here, and you can add and subtract u infinity here. Okay, once you add and subtract u infinity, I'll show you why this is called a displacement thickness in the next lecture. So we'll continue we'll continue from this point.